So in geometry, we deal a lot with something called conditionals, or things called conditionals. So let's talk real quick about what a conditional is. As you can see on the screen, it says a conditional is an if-then statement that relates a hypothesis, which is the part that follows if, to a conclusion, which is the part that follows then. So for instance, if I were to say, if I have 4 quarters, then I have $1, that would fit the definition of a conditional because I've kind of made this if-then relationship between two separate statements. A lot of times we see this notation used for representing conditionals, this little P and then a one-sided arrow pointed to the right and then a Q. And if you see a symbol like that, you would read that as saying if P then Q. P represents whatever phrase is the hypothesis, and Q represents whatever phrase would be the conclusion. So that's what a conditional is. So let's look at our first example in this section. It says write the statement as a conditional. You can register to vote if you are at least 18 years old. So what we're looking to do here is turn this statement into something that means the same thing, but starts with if, and then there's a phrase, and then a then, and then there's a phrase. So if we look at this, we can see, okay, I see the word if in there. If you are at least 18 years old. So that would be my hypothesis. The part that happens after that, so what happens if you're 18 years old? Well, then you can register to vote. So our if-then statement, our hypothesis would be if you are at least 18 years old. Our conclusion would be you can register to vote. So our conditional would turn out to say if you are at least 18 years old, then you may register to vote. So I would encourage you now, there's a couple more examples that you can get through your interactive student edition. I would encourage you to go through and take a look at those and try those different examples of just taking a statement that's not written as an if-then statement and converting it to an if-then statement. The next thing we're going to look at is figuring out whether or not a certain if-then statement is true or not. So for an example, now they do a little thing with here in your textbook with something called a truth table. We're going to kind of ignore that for the most part in this class. You can take a look at it and try and go through that if you want, make some sense of it. But to save a little bit of time, we're going to ignore that and just kind of talk about these things a little bit differently. So how can you determine the truth value of this conditional? In other words, is this a true statement? If a number is even, then it is divisible by 2. And when you have an if-then statement that you're trying to determine whether or not it's true, what you're really looking for is, well, if the hypothesis part is true, does the conclusion part always end up being true? And if the answer is no, sometimes the hypothesis can be true and the conclusion can be false, then our answer is nope, that is not a true statement. All right, and that's what this is saying up here, is when your hypothesis is true, does that make the conclusion true? If that's the case, then our conditional is true. But if your hypothesis can be true, and then your conclusion can somehow end up being false, then our conditional is false on the whole. The whole thing is technically considered a false statement. So here's an example. If a number is even, then it is divisible by 2. So we would think, okay, let's say I have a number that is considered to be even. Will it always be divisible by 2? Or is there some situations where a number is even and it's not divisible by 2? Because if it's always divisible by 2 when it's even, then this is considered a true statement. But if there were some instance where it would not be divisible by 2 when it's even, then we would have to say this is a false statement. And so the answer here, we can see, is that the conditional is true. An even number is always divisible by 2, so when the hypothesis is true, the conclusion is true, and so the whole conditional is true. Now here's another one that says, if a quadrilateral has 2 pairs of congruent angles, then it is a parallelogram. So the question would be, okay, is it ever possible for a quadrilateral to have 2 pairs of congruent angles and not be a parallelogram? And in this case, the answer is yes, it is possible. It's called an isosceles trapezoid. And in this isosceles trapezoid, you can see that we have two pairs of congruent angles. This pair of angles are congruent, and this pair of angles is congruent. And so we've figured out a situation where the hypothesis is true, but the conclusion ends up being false. And so because of that, the conditional itself is false. And here's a couple other examples. I would encourage you, again, to try these on your own, see if you can come up with the correct answer for these. And then we'll move on to another idea of related conditional statements. So a conditional says if P, then Q. But if we play around with this P and the Q and the direction of the arrow and things like that, then we can create a few different kinds of statements related to our original statement. So to start with, the converse of the statement. This is what happens when we take the hypothesis and the conclusion and we switch them around. So whereas if our original statement said if P, then Q, our converse statement says if Q, then P. So to give an example, let me pull up my pen here. If I said, if I have 4 quarters, then I have $1. Oops, I didn't pull up the pen. I pulled up the wrong tool. So if I said, if I have 4 quarters, then I have $1. There we go. Now let's try it one more time. Here we go. If I have 4 quarters, then I have $1. That would be my if P then Q statement. My converse statement would say if I have $1, then I have 4 quarters. So you can see all I did was switch around where the conclusion and the hypothesis are. And that's called the converse of a statement. Now to negate a statement, it's indicated with this little symbol here, the little tilde symbol, means to just say the opposite of what the original statement was, or not the original statement. And we use the negation in the next couple of related conditional statements. The next one we have is called the inverse. And to write the inverse of a conditional statement, we keep the P and the Q in the same order, we just negate both of them. So up here, I would say something along the lines of, if I do not have 4 quarters, then I do not have $1. And that would be the inverse of this original statement. The contrapositive is like the combination of the converse and the inverse, because what we're going to do is we're going to switch the P and the Q, switch the hypothesis and conclusion, and negate both of them. So the contrapositive of this statement would say, if I do not have $1, then I do not have 4 quarters. And that would be considered the contrapositive. So let me clear off my writing here, clear that away, and then let's go to the next slide. So the next slide says, write and determine the truth value of the converse of this conditional. If you play the trumpet, then you play a brass instrument. So converse, remember, all we do is we switch the if part with the then part. So our solution, our converse of this statement, would simply say, if you play a brass instrument, then you play the trumpet. So now the question is that a true statement? If I say, yes, you definitely play a brass instrument, does it have to be true that you play the trumpet? And the answer would be no. You could play a brass instrument and play some other instrument that's not a trumpet. You could play the saxophone, for instance. So this converse statement would end up being false. And so that's something you're going to find, is that we have all these related statements, the converse, the inverse, and the contrapositive, and just because your original statement is true, that doesn't guarantee that the other related statements will also be true. Some of them might still be true. You know, if your original statement is true, maybe your converse is true. Maybe your contrapositive is true. But if your original statement is not, or is true, some of these might still be false. All right? And that's what we saw in example 3 here. Now, I believe under example, let's see, there we go. Under example 3, there is another example, a couple more examples for you to try. I would encourage you again to look at this. For instance, example 3a here says, if a polygon is a quadrilateral, then it has 4 sides. What would the converse of that be? Well, it would be if a polygon has 4 sides, then it is a quadrilateral. And then so you would think, is that true? Does every 4-sided polygon fit under the category of quadrilateral? And the answer would be yes, it is. And then so I'll let you try letter B on your own. And let's take a look at our next example. Oh yeah, this next example is a video. So I'm actually going to have you guys watch that on your own. It has to do with doing the inverse and the contrapositive of this conditional here. If two whole numbers are even, then their sum is even. So the inverse, remember, means that we're just going to keep these in the same order, but negate both of them. So it would say something like, if two whole numbers are not even, then their sum is not even. So you'd think, okay, is that true? Can I have two whole numbers that are not even and have a sum that is not even? And then the contrapositive would reverse these two. So it would say, if two numbers' sums are not even, then the two numbers are not even. So contrapositive reverses them and negates them. So you can go through those, try and see if you can figure out the answer to that question. There is also another example. If today is a weekend day, then tomorrow is Monday. What would the converse, inverse, and contrapositive be? And which ones are true and which ones are false? I would encourage you to try that. And lastly, oh, well, we got a few more. Biconditionals. So biconditionals are statements that work in both the original format and the converse. So I could say, if today is Monday, then yesterday is Sunday. And I could also say, if yesterday was Sunday, then today is Monday. So both the original statement and their converse are both true. And that fits under what's called a biconditional. And sometimes we write biconditionals as saying, P if and only if Q. So as an example of what one of these might look like, a marine biologist writes this conditional. If a seahorse gives birth, then it is a male. Since it is true that among seahorses only the males can become pregnant and give birth, should the marine biologist state this as a biconditional in a paper she is writing? And so we would identify what our hypothesis and conclusion is, and then combine them in both directions. So the hypothesis would be a seahorse gives birth. The conclusion is a seahorse is male. And so the biconditional of this scenario would say a seahorse gives birth if and only if it is male. And then so we would look at that as two separate statements. If a seahorse gives birth, then it is male. And that's true because in nature, seahorses, only the male seahorses give birth. So that one's true. But then the second part of that is where we flip it around and write the converse. If a seahorse is male, then it gives birth. That's actually false because not every male seahorse perhaps is going to give birth. So that part of it is false. So to answer our original question, no, the biconditional that would come from that would not be true. So the marine biologist should not include that statement as a biconditional in her paper. Now there's one more example for you to look at here. It says, well, we can quickly do this one together. A triangle is equilateral if and only if it has three congruent sides. So what two conditionals come from this? Well, we would say if a triangle is equilateral, then it has three congruent sides. But then we can switch that around and say if a triangle has three congruent sides, then it is equilateral. And so the answer to both of those would be yes, that's true. Every equilateral triangle has three congruent sides, and every triangle that has three congruent sides is an equilateral triangle. So in this instance, the biconditional that we started with, a triangle is equilateral if and only if it has three congruent sides, that does end up being true. The last slide here is just a summary of everything we went through, so you might want to take a look at that real quick. But other than that, that's about it for Section 5. I know some of this we went through pretty quick. Hopefully, as you try the practice problems, some of this can kind of maybe clear itself up a little bit. If not, make sure you come and ask me any questions that you have during class. All right? Talk to you later.